All right, so this is going to go through the Unit 4 review guide. And what we were doing in Unit 4 is talking about the mole concept as it applies to kind of almost everything that we do in chemistry, and how we can relate different quantities of things to one another through the use of the mole as a bridge between units. So this was the mole map, so to speak, that we developed, but we were able to use this to kind of have a visual representation of those jumps that we can make from different quantities. And of course, the mole connects all of those quantities, those being mass in grams, volume in liters, and of course particles, whether that's molecules or atoms, in terms of a number amount of something. And it was important to note that the only reason we can use that 22.4 liters value is because we are identifying that everything is at standard temperature and pressure, or STP, when we are analyzing these problems. So that's why we can assume that there are 22.4 liters of gas whenever we're using it, equal to 1 mole there. So let's hop all the way back up, and let's just start going through these conversions. So remember, anytime we're talking about a conversion factor, we're talking about something that we can go from one unit to another with. Of course, between moles and number of particles, we know that there is 1 mole equal to 6.02 times 10 to the 23rd particles. And particles can be atoms individually, or molecules as a whole. Right? It could be one or the other, doesn't necessarily matter. So we use particles as an all-encompassing unit, so to speak. Mole. 1 mole is equal to, when we're talking about grams, anytime we talk about grams, we need to find the molar mass in grams. And of course, we find it from the periodic table, right? And those are the average atomic weights of each of those elements, and then we can equate those to 1 mole in terms of how much those things weigh per mole of that. And that's why we have grams per mole, of course, is the unit there. All right, but last but not least, liters at STP. Again, that just means standard temperature and pressure. That means that there are 1 mole, or is 1 mole equal to 22.4 liters of gas, whatever gas we have. So you could see that the only conversion factor that's going to have a different value equal to 1 mole potentially is the molar mass, because that depends on what the actual substance is that we're looking at. But as you can see for our particles and our liters, right, that number for liters is the same for every substance that we're using. That number for particles, the same for every substance that we're using. So the only one that's really going to vary, again, is molar mass. So let's do a couple of things before we get to that. We want to identify which one has the greatest molar mass. And of course, finding molar mass is very similar to going shopping. If you go to shop, you want to buy one of everything. Each thing costs some certain amount, and you get a total in the end. And that's kind of what molar mass is. So we use the periodic table values to figure that out. So let's do C2H6 over here, and let's do CH2O over there. We have carbon, we have hydrogen. Carbon weighs 12.01 grams. Hydrogen weighs 1.01. I'm going to multiply each by how many I have. We get 24.02. We get 6.06, and then we add them together, and we should end up with 30.08, of course, grams per mole. All right, so that is for C2H6. And now we have to hop on this substance over here, CH2O, do the same thing, identify how much of each thing we have. We have 12. There's only one of the C's there, so we only have 1 carbon to worry about. We have 2 hydrogen, which are going to give us a mass of 2.02 for hydrogen, and then, of course, 16 for oxygen. You add all that up together, you should end up with 14.03, and then, of course, it should be 30.03 grams per mole, if I'm not mistaken. And so we end up identifying which one has the greatest molar mass. Then we would say, well, it is C2H6 because it has a greater mass per 1 mole, which is what molar mass is. All right. So moving on to the next one. Now we're going to start to talk about our actual conversions, and we use dimensional analysis, or what we just call a technique to convert units based off of what we're starting with and what we want in the end. So I like to always annotate, underline what I have, and try to identify what I'm looking for, and that helps me, especially with the mole map, identify how many jumps I need. Well, if we wanted to use the mole map for this first one, we have 3.9 moles is what we're starting with. Of course, it's of lead. Put that first one over 1, just the number, no unit associated with that, just to show that it is in theory, a fraction. Therefore, on the unit and the number that we have is on top. We say on top because, of course, we look and see how many bridges we need to jump on our mole map to identify how many conversion factors we need in order to go from mole to particle. So if we roll all the way down here, we see that we're starting with the unit of mole. Let me put the laser pointer here. Starting with the mole, we want particles in the end. We only have to jump 1 bridge, which means we only need to include 1 conversion factor, which means 1 additional fraction, so to speak, in our problem here. And so we get 1 fraction. Now, in order to cancel units out in dimensional analysis, the same unit has to appear diagonal of each other. And then the unit in question, or the unit that we want in the end, has to be on top. And we know that all of these conversions in this unit are equivalent to 1 mole, so the number 1 will travel with the unit of the mole. And then we have, of course, 6.02 times 10 to the 23rd particles equivalent to each mole. And so how do we put this into the calculator? Well, there we go. Remember, and you're going to be using the TI-84s, I believe, but you can simplify everything, and we simplify everything by multiplying top numbers and multiplying bottom numbers and then dividing in the end. In this case, you see that the 2 bottom numbers are just 1, so truly we don't have to do anything with those because multiplying by 1 is just 1, and then of course, and I don't know why I can't touch that. Sorry. There we go. Multiplying by 1 is just 1. Dividing by 1 is whatever the number is, so we don't have to worry about that. So we just do 3.9 times. Now, inputting into the calculator, there's a nice way to do that. We have a special function for the scientific notation values here. It's 6.02, and second comma gives us that E, so to speak, for exponent. And then we have 23, and now we just solve. And so hundredths place is good for any rounding. So we have 2.35 here. And then, of course, we cannot forget times 10 to the 24th there. Of course, the unit, too, is particles. All right, so let's do another one. Now, anytime I see the word grams, I immediately want to look and see what my formula is for my substance, because I'm going to need to use that to calculate the molar mass of my substance in order to have a conversion to be able to use to go to mass or go from mass. So what's the mass in grams? Well, barium and oxygen. Barium, if we look on the periodic table, I believe has a mass of 137.33, and oxygen has a mass of 16. Right, add those two together, 137.33 plus 16. That gives us 153.33 grams per mole. And now we run over here, and that we keep to the side for now until we need it. Remember, that's going to be how we can go from mole to gram or gram to mole or vice versa. So we identify that we start with a particle number, and then we want mass in the end. So this is going to be a particle to gram conversion problem. So if I go to my map, particles to gram, I'm starting down here in this island, so to speak, and I want to get up to mass. So in order to do that, I have to go from here and to the mole unit first, right? Remember, I cannot go directly from number amount to mass, so I need to have a unit that bridges that gap, which ends up being the mole here. So I identified that I'm going to have to cross one bridge, which is one conversion factor, and then another bridge, which is a second conversion factor. So unlike the last problem that we just did, where we just crossed one bridge, we're actually crossing two. So when I set this up, I actually know that because I'm going to use two conversion factors, I need two additional fractions, extensions or so, to my problem here. Because I'm starting with particles, I put it over 1. And here are my two conversion factors that I'm going to need to use. And I let the units take care of themselves. Particles is what I start with, so I need it to go away in order to get to moles. And then moles will go away in order to get to grams. And then I can solve from there. So let's just add numbers in. Well, we know that all of our conversion factors are equal to 1 mole. There are 1 mole equivalents. So number 1 travels with the unit mole. I know that there are 6.02 times 10 to the 23rd particles in every mole. Particles go away as a unit, like moles went away up there. And of course, I know that 153.33 grams are equal to 1 mole for this specific substance in barium oxide. Mole goes away as a unit. So what I was talking about before with simplification is we can actually just take the top numbers, multiply them together, and take whatever's on the bottom, multiply it together to get just two numbers in the end that we have to divide by. So 3.82 times 10 to the 23rd. You'll notice I'm using parentheses every time I have scientific notation just to make sure that my calculator knows to keep track of order of operations and keep those straight. So I end up with 5.886. It's rounding too soon, but for say how big this number is, it doesn't necessarily matter with what we're going to be wanting as an outcome. And then, of course, at the bottom, it's just Avogadro's number there. And so we take that value, 5.86 times 10 to the 25th, and divide it by 6.02 times 10 to the 23rd. And we end up with 97.34 grams. All right, grams specifically of barium oxide there. All right. So in this next problem, we see that we have we're starting with grams this time, right? You're always looking to see what you have a number value for on top of the unit itself. And so we see we have grams to start, particles here. Sample of, and in this case, because we see that word gram, we immediately want to refer to the periodic table to calculate the molar mass, because that's how we're going to be able to convert grams to moles in this case to get to particles, right? Counting by weighing. So we need to know what the equivalent mass is equal to 1 mole of this substance right here, calcium nitrate. Well, calcium, nitrogen, and oxygen. All right, 40.08 grams per mole for calcium. There's only one of them here. Nitrogen weighs 14.01 grams, and there are two because this 2 out here tells us we have 2 nitrate groups. So we have 2 Ns, which gives us 28.02. And we have oxygen, which weighs 16 grams. However, because there are 2 nitrate groups, 2 times 3, that is going to give us 6. right, which will give us 96 here. If you want to see the actual math here, right, I'm going to do 40.08 plus, and then I'm going to do it all at once. So I'm just going to take the mass of nitrogen, multiply it by 2. That's how we get the 28.02 plus 16 times 6, and then we end up with 164.1 grams per mole. All right, so that is the molar mass, and notice how this molar mass is different from barium oxide above, and that's because it's a completely different substance. It's a different compound, so it's going to have a different molar mass, but we do have the same value for the particle to mole, right? The only one that would change is the molar mass values equal to 1 mole. So starting with grams, 97.8 grams over 1, just to show it's a fraction. And I know that I'm going to need 2 conversions again because just like before, we can't go straight from grams to particles, again, also per our mole map, so we have to go to the unit of mole first. And grams will cancel out moles on top. Moles need to cancel out for particles to be on top. And so we just add in the values that we know. We calculated 164.1, 6.02 times 10 to the 23rd at the top. Let's simplify and solve. 97.8 times 6.02 times 10 to the 23rd gives me 5.88, actually 89 times 10 to the 25th, and 164.1 on the bottom, and divide those two values, 5.89 times 10 to the 25th divided by 164.1. And we end up with 3.59 times 10 to the 23rd particles. All right, a couple more. Find the volume occupied in liters by this many particles. So we have this many particles of nitrogen trihydride. We're trying to find volume now. And so what we can do is identify how we're going to get from particles to volume. And we use the periodic table. Actually, not the periodic table this time. We see that we're starting here in particles. We need to go to volume. There's only one way to do that, and that's to get to the unit of mole first, right? Cross one bridge, and then we're going to cross the other one. So since we're crossing two bridges, we're going to use two conversion factors. And so we set that up just like we did above, 8.97 times 10 to the 23rd particles over 1. And I will have two conversion factors to utilize here. And particles go to mole, moles go to liters, and then I know that those conversions are equivalent to 1 mole. There are 6.02 times 10 to the 23rd particles. There are 22.4 liters per 1 mole. And again, I forgot to do that up here, but the units will cancel out, and I'm left with the unit that I want in the end on top. And simplify. So we have 8.97 times 10 to the 23rd times 22.4. That gives us 2.01 times 10 to the 25th. And then, of course, Avogadro's number is now on the bottom because that's where our unit of particle needed to be. And we take 2.01 times 10 to the 25th divided by 6.02 times 10 to the 23rd. And we end up with 33.39 liters. All right, and something that's of note here is, for the other two problems, I calculated the molar mass. I went right to it, and I did not do it for this one, even though I gave you a formula. That's also because Nowhere in this problem here in number 8 does it ask about grams, whether to have grams to begin with or to find grams in the end. And because of that, we don't need to find the molar mass because that's not going to be a conversion factor that we need to use. So don't do more work than you need to, and don't worry about the molar mass for this one, right? Because we have set values for those particle and liter conversions. Now, in this next one, number 9, we see we do start with grams, and so now we know, okay, we are going to have to take note of what the substance is and find its molar mass here, because that's going to be a conversion factor that we use. We want liters in liters, and so before we do anything, let's figure out what the molar mass of this is going to be. We end up with, just 1 carbon, 2 oxygen gives us 32. And then, of course, that's going to give us 44.01 grams per mole. So there's our molar mass for our conversion factor. So we start with what we're given, 27.2 grams over 1. And then identify that on the mole bridge or mole map here, we see that we are given grams, right? And so we want to get to volume similar to before. We have to cross 2 bridges, which means we're going to need to use 2 conversion factors, which means we have 2 fractions extended on our problem here, right? 2 conversions, 2 fractions. And grams go away on the bottom to get to moles. Moles go away on the bottom to get to liters. 1 mole apiece. And, of course, our molar mass that we found to be 44.01 grams, 22.4 liters on top. And all units go away except for liters, which is what we want in the end. 27.2 times 22.4 gives us 609.28. divided by 44.01, and our final answer is 13.84 liters. All right, so we did that pretty quickly, all things considered. And so now what we're going to do is jump over to some percent composition. So we did a lot of unit converting at the beginning of the unit, and then we started to get into percent composition, which is truly just taking the molar mass to get the total mass of our compound, and then figuring out how much percent of that compound is made up of each element that makes that compound up. So really, the percent comp equation is just the individual over the whole, like any percentage, times 100. So the individual mass that one element contributes out of the whole. And of course, I'm not going to do all of these. I'm pretty much just going to do the first one. One thing that I will note a little bit later on when we get there is ammonium nitrate in that formula. But lithium phosphate, so let's do one example of these. Lithium phosphate, and we have to first figure out the total mass. So the total mass is going to be based off of lithium, phosphorus, and oxygen. Lithium weighs 6.94 grams per mole. Phosphorus is 30.97 grams, and oxygen is 16. I'm going to multiply everything by if I have more of it or not. I have 3 lithium to worry about. I only have 1 phosphorus. I have 4 oxygen. So let's figure out how much each of these are accounting for the mass by themselves, how much mass each thing has. So my 3 lithium are contributing a total of 20.82 grams. My phosphorus is, of course, just contributing its 30.97, and then my oxygen is contributing 64 grams to the mass as a whole. So let's add all these up to get a total. And I'm actually going to put that total down here. So we're going to add up the 20.82 plus 30.97 plus 64. That gives us 115.79 grams per mole, right? That's the total molar mass. So we're going to use this value as our whole, right? That's going to be the whole. And then to get the percentages, we just kind of plug all of the individual contributions over that. So for the percent of lithium, we know that lithium by itself is 6.94 grams, but because we have 3 of them, we have to use the total mass that lithium itself contributes, which is the 20.82, and divide it by 115.79 times 100. So, of course, in any percentage, we'll multiply by 100 to obtain the percent. 115.79, hello. Times 100, and you'll see that all we're doing is moving the decimal 2 places to the right. So we get about 17.98% there. Let's do the percent of phosphorus. Phosphorus, there was only 1, so there's only 30.97 grams contributing, but the whole is the same, right? It's the total molar mass. 30.97 divided by 115.79, and whoa. And then times 100 to get that percentage. That 6, we can bump up that 4. So 26.75. Right? Normally I'll have you just go up to the nearest tenth for percentages. And then oxygen. Now, of course, you can find oxygen one of 2 ways. You can take these two, add them together, and then subtract whatever that answer is by 100. That is always a valid way to do the last element percent if you choose. Or you can just continue to stay the course and do exactly what we did before. It works either way. And you should end up with 64 divided by 115.79 times 100, and that gives us 55.27 percent. And ideally, if you add all those up together, you should end up with 100% anyway. So that's a way that you can check your work, but there my percentages go. So again, individual divided by the whole. I guess the hardest part here would be if you're looking at something like ammonium nitrate, where it can be very easy to miss that this N and there's also that N. So there's a total of 2. You don't have to do them separately. You just say, oh, well, there's 2 N's, even though they might be part of different polyatomic ion. They're still both the same weight, and there's that many of them, right? So you can just make sure you don't miss that there's 2 nitrogens there. But yeah, then you can check yourself to the key for the next 2. But I would prefer to focus on some more empirical formula, and we're not going to worry about molecular formula right now. So just the empirical right now. And again, I'll do maybe 2 of these. Just note that we do have our conversions, right? We're able to say if it's like 0.9, you can round up. 0.0 or even 0.1, sometimes you can round down to the nearest whole number, but if you end up with something that's 0.5, you have to multiply by 2. 0.33 or 0.66, you multiply everything by 3. 0.25 or 0.75, you multiply everything by 4. Again, just because we can't have non-whole numbers as our ratios for our moles here for these formulas. So the way that we've kind of done in class was to just kind of take it step by step and just lay out everything that you have. And we have, in this order, these percentages of these substances, or these elements. So we have carbon, we have hydrogen, and we have oxygen. We have 26.1% of this is carbon, 4.3% is hydrogen, 69.6% is oxygen. Now, what we did was we're assuming that all of this is in a 100-gram sample because 100 grams out of the 100%, you could actually just call each of these percentages that many grams of that substance. So all we're doing is dropping the percent symbol and writing in grams here. Now, what we're going to do is we're going to then convert these to moles because they're not gram to gram ratios, they're mole to mole ratios within the formula of a chemical compound. So we're going to take all of these over 1, just like we would any of our other conversions. And the conversion that we're going to use, of course, says we need to go from mass to mole, the molar mass for each of these elements. Grams go on the bottom to cancel out, moles on top. And we know that all molar masses are equivalent to 1 mole of that substance. There we go. Now we just have to find the molar mass of each individual element. C is 12.01, H 1.01, and oxygen 16. So what we're going to do, and you could simplify if you want, again, this would be like 26.1, just over 12.01. So you can do that as a separate step. I prefer just skipping that, just knowing that I'm going to take that number 26.1 on top and divide by 12.01 on the bottom. And remember, this step right here, when you're calculating moles, make sure to go to at least 3 decimal places or the thousandths place. Because if you round too soon, you start to cut off your ratios and your numbers don't start to be as nice and you start running into some problems. So I'm going to say that this is 2.173 moles of carbon. I'm going to do the same thing for the others. 4.3 divided by 1.01, 4.257, 4.257. And 69.6 divided by 16, and we get 4.3. All right. And so now what I have to do is I have to identify out of those mole values, right? Because we just calculated moles, which one is the smallest? And we identify that the smallest is the 2.173. And so that's what we're going to use to create our mole-mole ratios. So we're just going to divide. Oh, I'm sorry, that was 3.5. Whoa. All right, so at this step, this is where we start to develop those ratios, which are going to act as the subscripts of our formulas, right? How many of those atoms do we have in there based on those percentages? One of these is always going to end up being 1 because you're always going to be dividing the smallest one by itself, and then the other 2. So we have 4.257 divided by 2.173. Now you'll see that 1.96, that is close enough, right? If we look at our thresholds up here, those decimals, if we're like at 0.9, we can just round up and round it to the nearest whole number upward, which is 2. And then we have 4.35 divided by 2.173. Hello, I keep doing that. Then we get like 2.00, which of course, 0.0, you just round down to the nearest whole number and you end up with 2. All right, so we didn't have to worry about any of these other multipliers because all of our ratios here, this one, and this one, we're able to work out pretty nicely. All right, there were no 0.5s, 0.33, so on and so forth. And so we just write out as is what the subscripts were in that order. So we had carbon, and only one of them, so we don't write a subscript. Hydrogen, there were 2, and oxygen, there were 2. All right, and that would be the empirical formula, the simplest ratio between those elements inside this compound based on their percent composition alone. Let's do number 12. number 12. And then I believe that this will be at least a good starting point for you to help you kind of through the rest of those. You can always check number 13, A and B to the key as well. So let's do this next one just as, another example. So again, we start with the percentages of each element that we have in our formula. We have nitrogen and we have oxygen. Nitrogen, there is 30.45%. Oxygen, there's 69.55%. We know that we're working out of a 100-gram sample, which means that we can just convert those percentages and call them grams. And then, again, you don't have to do over 1. That's just how I show that in our conversions for units, that number that we start with is effectively on top, like we like to say. And so we need that unit there on bottom in the next step to cancel out. And, of course, this next step, we're just converting those grams to moles. We know each molar mass is equal to 1 mole. And we say nitrogen weighs 14.01 grams for every mole. Oxygen weighs 16 grams for every 1 mole. And now this is the step where we are going to make sure we don't round too soon. So about the thousandth place, or 3 points after the decimal. 3 numbers after the decimal. 30.45 divided by 14.01. And we get 2.173. So 2.173. And again, you can add a fourth too. The more precise you are, usually the better that the ratios end up working out in the end. 69.55 divided by 16 gives us 4.347. 4.347. And that does kind of make a difference. So if you were to keep that at 6, you see the number right after that. I don't know if I can, I can't go to individual numbers, but the number right after the 6 is an 8. And so that's pushing that up if we round at that point to that 7 there. If you keep it at 6, that could also affect the way that your ratio outcome looks, because that is truly closer to 4.7 than it is 4.6. So just keep that in the back of your mind. But at this point, we only have 2 elements, so we've identified the mole amount of each based on the mass of each, and we identify that nitrogen has the fewer moles, so we're going to divide by that, and we're going to get our ratio where we have 1, of course, there for the nitrogen, and then we're going to take 4.347 and divide it by the 2.173. Oh, I was like, well, what is going on here? Divided by. You need to put the division sign in there. 173. That gives us about, right, 2.00, which, again, you don't have to write. If you can see from the calculator, that is basically 2. So then what is the empirical formula? I had 1 N. I had 2 oxygen. Right? So, again, in an instance where those values were not 0.5s or 0.33s, we didn't have to do any alterations with our conversions here. So, again, it's not going to happen all the time, and when it does happen, just identify what your decimal is closest to, right? If it ends up being 1.47 or something like that, well, it's probably closest to 0.5, right? Or 3.68 is definitely closer to 0.66 than anything else. So that's how you can kind of identify when you would use one of those values, and then when you would have to do the multiplier to fix those whole values. So I believe we should be pretty set with the empirical formula there. One thing I want to mention here is I give you all of the percentages here for your substance, and then the remainder H just means, of course, you can add all of these up, and then whatever that is equal to, just take 100 minus that. 100 minus all of these added, and that's how much H or hydrogen you have in here. So just a little, extra step, but not too crazy. So again, you could check a key to A and B if you want. And of course, I can go over any questions you have on those. But we'll just do this bottom part just because it's a nice little review. Identifying ionic or covalent. Remember, ionic is a metal plus non-metal, and you balance charges. Covalent are non-metal and non-metal. There's no charges, but we use prefixes, right? And so that's the idea behind those two. You can also add no prefixes to the ionics. You can add no charges or no ions for the covalents, right? Or else they would be called ionics. So I usually just use the first one, the first element, to identify what I have, ionic or covalent, because if it has a metal, the metal is going to come first, and therefore, unless it's, of course, ammonium, which is still an ion, it will be ionic. So calcium's a metal, it's ionic. Phosphorus in this next one is a nonmetal, that is covalent. Sulfur in the name is a nonmetal, that's covalent, but also we see that there are prefixes, so that also tells us that is covalent, because ionics don't use prefixes in their names. Copper, that is a metal, so that is ionic, so specifically a transition metal. Magnesium is a metal, that's ionic. Carbon is a nonmetal, that's covalent. And so now that we know which is which, now we can just use let me get this out of the way. Now we can use the rules, the appropriate rules, right, for each. So for the chemical formula, calcium's positive 2 ion charge. Nitride is nitrogen, which is a negative 3. If I crisscross those charges and make things easier, I know I need 3 calcium for every 2 nitrogen. And nitrate, right, nitride is N with a negative 3 charge. If it was nitrate, then it would be NO3 minus 1, or nitrite, NO2 minus 1. So again, you have to make sure you're paying attention to that suffix there. P, well, that's phosphorus, and there's 4 of them, so this is actually tetra phosphorus. And then 10 is deca, and hydrogen changes to the ending to hydride. Trisulfur, S3, hexachloride, Cl6. This one, copper, is the transition metal, and immediately you're saying, oh, copper's a transition metal, so there's 2 of them, right? So Roman numeral 2, I know I have to put a Roman numeral there. Well, that is not necessarily correct, because the Roman numeral represents the charge that the transition metal takes, not how much or how many transition metals are in the actual formula itself. And so we can work backwards using this. We can say, well, I know sulfur is always a negative 2, so it has a negative 2 charge. And I know that the overall positive charge must be positive 2 to balance this out in the formula. Well, if I take 2 and divide it by how many there are, then I see that each copper has worked the positive 1 charge there. So my charge on copper is 1. So this is copper 1 sulfide. Sulfide because sulfur is by itself. That's why it's not sulfate. If it were sulfate, it'd be an SO4 group, right? Magnesium, plus 2. Phosphate, and like we were talking about, it is not P by itself. That would be phosphide. All of our 8s and 9s are on the list in the back of the periodic table. Phosphate is actually a PO4 group, minus 3. So this is a case where the polyatomic has the same charge as the general element there. And so we, again, can crisscross, but we see that we'll need 3 magnesium. And because we'll need more than 1 phosphate group, we have to show that that 4 sticks with it, and that we need 2 of the entire group itself. So that's why we put polyatomics in parentheses if we need multiple. This next one's covalent, so we're just using the prefixes, di, carbon, and 4 is tetra, tetraoxide. All right, so I hope this helps. Again, check your work to A and B here. Also, with the dinitrogen trioxide and the ammonium nitrate there, just to double check that you're on the right track. But hopefully this gets you started and helps you out a little bit. So if you have questions, bring them with you. But that is all I got.